Okay, I'm still working on the exams, and I'll get those back. I'll probably get those posted tomorrow. Okay, and then I can pass them out on Wednesday. Now, we had a deal that y'all were going to watch lecture 14 online, and I'm sure you did that, but I do want to go through it and hit a few of the highlights just so that I can emphasize the things that I really want to emphasize in that lecture. And then we'll do 15 today. So we're going to do two quick ones, two quick PowerPoints, but let's jump in since we're going to be pushed for time a little bit. Okay, so this again is dealing with the equations related to vibrational spectroscopy. This is the harmonic oscillator. That's the potential that we have. And for the harmonic oscillator, that's a parabola, and it goes to infinity. And that means the bonds would never dissociate. So, but we know that that's not realistic, right? If I pull on a hydrogen atom and a carbon-hydrogen bond, it eventually is going to come off. It's not going to stay bonded to that carbon with the potential energy that goes to infinity. So that's what we have where this starts to taper off, and in this difference you have the bond energy. But down here at the bottom, the harmonic oscillator approximation works pretty well. And most of our vibrational motions are in the ground state. If you were to take Boltzmann's factor or Boltzmann's constant and see how many joules you have, if you wanted to convert that to wave numbers at room temperature, that's a way to convert joules to, or Kelvin to joules. And then you can convert the joules to wave numbers. Room temperature has about 200 wave numbers. Okay, so when you've got a CH stretch, that's 3,000 wave numbers. The difference between the ground state and the first excited state is 3,000 wave numbers. So at room temperature, you have no way of exciting that bond. So that's just saying that all of these bonds, unless they're down at 200 wave numbers, are going to be in the ground state. And so we're not going to have hot bands. And so this harmonic oscillator approximation works really well for all of our molecular motions. And that's really odd because if you think about, we've been talking about quantized effects and everything behaving like waves, and the harmonic oscillator is a massive ball on a massive spring. We did that in mechanics, like classical physics. And so harmonic motion in the molecule, all of these vibrations of the molecules can be understood with a force constant for that bond length or that angle bend and the masses of the nuclei. So it is really very interesting that we would have such a classical model applied to something so microscopic. Now, the spectroscopy aspects of it require wave functions. Okay, so, but the vibrational frequencies, we could calculate those if we know the force constant and we know the masses of the atoms. Okay, now let's look at those wave functions. So if we zoom in, we'll see those quantized energy levels. The harmonic oscillator in classical physics is not quantized, but for vibrational motion in a molecule, it is. And so these would be those lower wave functions. They look kind of like the particle in a box wave functions, but not exactly. Notice in the particle in a box, we had zero potential energy in between the walls of the box, and then it went abruptly to infinity. And what is this wave function, or this potential energy surface? It's a parabola. So it goes smoothly to infinity. Okay, so it's narrow deep in the box, and it gets wider as you go up, whereas our particle in a box model was the same width all the way up. So when it was the same width all the way up, our energy levels went up by n squared. So think about that energy equation. Energy was n squared times h squared over 8ml squared. Okay, but the harmonic oscillator, the box gets wider as you go up, and L is in the denominator. So that allows those energy levels to come down to where it's just a linear dependence on quantum number. So the energy equation for this is just equally spaced energy levels. It's the quantum number V plus a half times the vibrational frequency. And so if I go from V equals 0 to V equals 1, I get another unit of that vibrational frequency in energy. And if I go from 1 to 2, I get another unit. And from 2 to 3, I get another unit. So it's equally spaced. And that's another unique thing about vibrational spectroscopy and the harmonic oscillator is that our energy levels are equally spaced. Okay, so we labeled the ground state and vibration as V equals 0. Definitely want to make sure you know that. So V equals 0 is the ground state in vibrational spectroscopy. What was it in the particle in a box? 1. And so you memorized, I'm sure, the fundamental is 1 to 2, didn't you? Okay, not here. The fundamental is 0 to 1. So it's more correct to say the fundamental is from ground state to first excited state. And to say if the ground state is V equals 0, then it's 0 to 1. And if it's in the particle in a box, the ground state is N equals 1, so it's 1 to 2. You see that? You got to be more precise in your definition of the fundamental. It's ground state to first excited state. So you got to know what your quantum numbers are. And all of the real systems, like vibration and rotation, they start with the quantum number 0. Okay, the particle in a box is weird, and then it starts with quantum number 1. So that was one of the reasons why I wanted to go over this again, to emphasize that. The symmetries of these are just like the 1D particle in a box. They're even, odd, all the way up. And so we have the similar selection rules. If light is odd and we're trying to go even to even, then that's not going to work out, because odd times even is odd, and then even times odd is odd. So they will have an odd integral at the end, and that'll equal to 0. But here, even to odd with odd light, that's going to be not equal to 0, so that would be allowed. So the fundamental is allowed. So it looks like we have the same selection rules, right? Delta V equals 1, 3, 5, and 7, and so on. So it has very similar symmetries to our particle in a box for vibrational spectroscopy. But one thing that we do have in vibrational spectroscopy that we didn't have in the particle in a box is this anharmonicity. So if we're using the harmonic oscillator for our sort of base assumption, when it deviates from that harmonic behavior, it's anharmonic. So an just is a negation, right? It's not harmonic. So that's what we're dealing with here. This is anharmonicity, when that potential energy function tapers away from a parabola. You can see that anharmonic energy levels are not equally spaced. So if you look down here, the fundamental, this is 0 to 1. You know, that matches. So these gold lines here would be the harmonic oscillator energy levels, and they're equally spaced. But notice when you get to 2 and 3, especially 3, you can see there's a difference here. The actual level is below the harmonic oscillator level, and 4 is even worse, right? So this is 4 here, and this is 4 here. So that difference is that anharmonicity coming into effect. So the higher you go in those energy levels, the worse it gets. Like the more the base assumption that it's harmonic fails. Okay, as you go higher in the quantum number. You have a couple of different dissociation energies too. So that's the energy difference between the either the bottom of the potential well and where the bond breaks, or the 0 state, so V equals 0. So D0 is the dissociation energy from the ground state to where the bond is broken, or if it's from the very bottom of the potential well to where the bond is broken, that's DE.
Bottom of the what line?
Potential energy well. So these curves are potential energy surfaces. So they're the potential as the bond vibrates. So let me start with the x-axis. I should have done that. This is the bond distance between the two atoms. Okay, and the y-axis is energy, potential energy. And so we can see those different curves. If I'm right at this equilibrium bond length, then I'm at the minimum. But it's not static. Every bond is always oscillating. And so it's oscillating around that middle position. And it would have this ground state energy. And that's about the width of its oscillation. That represents the width of its oscillation. It's going to go to the turning points on this potential energy curve. When it gets over here, it's going to turn around and go the other way. So it oscillates. So as I excite the molecule, it oscillates more. You see here, the turning points are farther apart. And if we get up here to the very top, look how far it oscillates. It's compressed a little bit, but it really stretches a lot. And then it turns around over here. And so think about this. I will just so my head is a big old heavy atom, and then I've got a little light atom here, like a HCl. So I got a chlorine here and a hydrogen, and it's oscillating. So this might be the ground state. Okay, and then it gets excited. And then it gets really excited, and you see it go out here like that and comes back. But you see how it spends a lot of time out there. And if it gets super excited, it goes out, and it never comes back.
And that's what's happening there.
At the very top, yeah. And so that's the dissociation energy. When I've given it enough energy that it's stretching way out there, it comes in and turns around, and then it never comes back. So that would be thermolysis. I've heated it up until it lyses, it breaks the bond. Or I could do it radiatively. I could hit it with enough like light to cause it to jump that far, and it would just break the bond. So here's our oscillator, our harmonic oscillator energy function. You can see V is the quantum number, and nu with the tilde, that's the vibrational frequency. So that little tilde means it's a vibrational frequency in wave numbers. Yeah, V inside the brackets is the quantum number. And remember how we did the, like with the transition equation, how we were pulling some of those constants out and leaving like a half, like a quantum number plus a half and so on. That's a common practice we see a lot. And here we see it in the energy equation. V plus a half is the quantum number. And that 1/2 is what we call the 0-point energy. It's kind of funny. Syndrome in The Incredibles talks about that 0-point energy, but he's not using it in a correct way, but he throws that term in there. So you've heard that if you watch The Incredibles. It has nothing to do with what Syndrome was doing. It's just this energy right here. That little bit is a half of the vibrational frequency. So if you have a vibrational frequency of 2,000 wave numbers, this difference here is 2,000 wave numbers. And this little half down here is only 1,000 wave numbers. So it's 1,000 wave numbers above the minimum of that potential energy well. Now, where do we get the frequency of vibration? Well, it's a function of the masses and a function of the spring, just like in classical mechanics. So if I have a heavier mass, I've got a lower frequency. So you can see that mu is the mass. It's the reduced mass. So whatever mass is moving, it's the effective mass of whatever's moving. And so you might say, well, for a bond stretch, it's easy. And yes, it might be a hydrogen that's just moving. So if I have a chlorine and a hydrogen, the reduced mass is essentially the mass of that hydrogen that's moving. But that's a pure vibration. Most of the time, vibrations aren't pure. There's some combination of masses. Think about water. So now my head is an oxygen, and I got 2 hydrogens. Okay, and it's doing this. What's the mass that's moving there? Right? It's not as simple as 2 protons. It's like some combination of those things. So, and what about 2 nearly equal atoms, and they're vibrating against each other? It ends up being half the mass that's moving. So, how do you compute that? Well, for the diatomic molecule, this is how you compute the reduced mass. Mass 1 times mass 2 divided by mass 1 plus mass 2. Anything other than a diatomic molecule is pretty complicated to calculate the reduced mass. And so that's what Gaussian does for us. So when we do those vibrational frequency calculations, you can see you have IR intensities, Raman activities. One of those lines in that output is reduced mass. So it'll calculate the mass that's moving, and you could use this equation to figure out, and it also gives you the force constant. So K is that force constant. So as the force constant goes up, so does the vibrational frequency. But as the mass goes up, the vibrational frequency goes down because it's in the denominator. And it's a square root dependence. So there's some homework problems associated with that. Sometimes those anharmonicity corrections come into play. And so you can see that energy equation up there. That's for the harmonic oscillator. This is for the anharmonic part. So we would subtract a little piece based upon the quantum number squared. And so we have this XE term, which is the first anharmonicity constant. And then that at higher quantum numbers tends to subtract too much. And so then we add a little piece that's based on the quantum number cubed. And we have a third term here, this YE. And so that would be the second anharmonicity term. And then if this adds too much, we might add a 4th term that's subtractive. So what we're doing is we're just giving it a polynomial fit. So we're taking the spectroscopy of these peaks and we're fitting it, and we're getting these anharmonicity terms. And the very last lab that you'll do in iodine, you'll actually solve for the XE term. So I know that's about a month away, but this is where we introduce it when we start talking about vibrations. Okay, so then we have these different molecular constants. I've highlighted a few. You're going to be solving for Iodine, you'll be solving for the vibrational frequency of iodine. So here's one of your literature values, 2214.5. And this dissociation energy, you're going to solve for the dissociation energy for iodine of 152. It'll be something on the order of that. And then for carbon monoxide, you're going to solve for the bond length. Now this is in picometers. There's like 100 picometers per angstrom. And so you'll have, your bond length will be 1.12. And they have 4 significant figures. You guys are going to get 6, maybe 7 significant figures out of your lab. Okay, so you'll get way more precise value than this. The force constant of 1902, and then this rotational constant of 1.93. You're going to get way better values for those 3 things. So it's kind of nice to see that you're actually going to do experiments where you could fill out a table like this. If you were to do that with all of these molecules, then you would know after this class how to calculate or how to experimentally measure all of these different values. There's lots of equations that go with these things, and the units can be somewhat confusing. So in that lecture, I talked about canceling all of the units. And so here I've put the equation up here, the vibrational frequency, and the force constant, and the reduced mass, and I've got all the different units of those in here. Here's the rotational constant and all of its units, and here's the energy equation and all of its units. And it's helpful whenever you're dealing with these tilde values. Those tilde values show that the number is in wave numbers. So right here, this wave number is indicated by this little tilde on top. And whenever you're canceling those wave numbers, you want to use the speed of light in centimeters per second. And so you might know this, you'll be off by a factor of 10 to the 2. And so if you're using meters per second, then you should be using centimeters per second. So I show a little bit about the force constants, because when you go into the literature, force constants are listed different ways, and also in Gaussian. Sometimes they're listed as dynes per square centimeter, dynes per centimeter, and sometimes they're listed as millinewtons per meter. And how to convert between those two. This is the slide that shows you how to convert between those two. Now, what's a dyne? Well, a dyne is a force in the CGS system. Okay, so from physics, let's see if your memory is good. So physics, the force equation, what is force equal to? F equals, mg or ma, I call it acceleration. We're in, so force equals mass times acceleration. And so here's our mass, kilograms, and our acceleration, meters per second squared. That's pretty cool, okay? So ma. Well, if you're using meters and seconds and kilograms, then you're in the meters, kilograms, second series of units. But sometimes it was sort of a toss-up whether they wanted to go with the meters and kilograms as the SI units or centimeters and grams. And so we have mass times acceleration in centimeters and grams, and that's the centimeter gram second system of units. So CGS. Well, this is a Newton here of force, and then this in the centimeter gram second, that's a dyne. It's also a force. So both of these are force values, but when you hear dyne, you're dealing with the grams, centimeters per second. If I were to take that force and act on a certain distance, like lift a weight a certain distance, let's take a kilogram mass against 1 meter per second squared acceleration force and move it a meter, then I would have 1 joule. Okay, so energy is a joule, mass times distance is a joule. And so that's energy. So this can give us energy. And it would be a joule. Okay. This energy here, do y'all know the name for the energy for the dyne times a centimeter? It's an erg. An erg. Strange sounding name, but you've used it before if you've ever talked about an ergonomic design. So that's where that comes from, the ergonomics, the saving energy, right? I used to be so sad Dr. White would have back problems, and I'd go into his office, and he'd have his computer here, and his mouse was way over here. And every time he's doing his mouse, he's leaning over like this. And I was like, no wonder you have back problems, because your mouse is over there. Get a keyboard tray. And anyway, so anyway, I go through this unit thing on the other video, and I just show how Newton per meter is 10 to the 3 dynes per centimeter. And so if you were to move that 10 to the 3 the other side, you end up with millinewtons per meter. And so if you see millinewtons per meter, that's the same as a dyne per centimeter. Okay, so let's look at these vibrational transitions. So 0 to 1 is the fundamental. That's what we just emphasized. And here's the transition equation. You see, I put in a 0 here and a 1 there for the quantum number. I did the difference. The halves cancel, and I end up with hc nu. So whatever the vibrational frequency is, that's where it shows up on the horizontal axis of the spectrum. So the vibrational frequency for a carbonyl stretch, like 1600, 1700, that's where that peak is going to show up. So that's also the frequency of vibration. 1 to 2 is a hot band. And anharmonicity allows all of the others. So we really have open selection rules for vibration. So we can go up 2 levels and 4 levels and so on because of anharmonicity. It breaks the symmetry. So those symmetry selection rules that were restricted and wouldn't allow plus or minus 2 or plus or minus 4 are broken because the potential energy surface is no longer symmetric. It does this. And because that breaks the symmetry, now we can go up to 2 and 4 and 6 differences in energy levels. Okay, those overtones are seen in the near infrared for the CH and OH stretches. The 0 to 2 is the first overtone. 0 to 3 is the second overtone. So if you memorized those things for the particle in a box, for vibration, they're slightly different, right? Okay, and then that first overtone transition it's almost twice the vibrational frequency, but there is a small piece that's subtracted due to anharmonicity. So it's typically it's very close to twice the frequency. So if the CH stretch is at 3,000 wave numbers, then the overtone, the first overtone, is going to be at 6,000 wave numbers, and the second overtone will be at 9,000. So just add up however many times of levels you're jumping. So samples can be solid, liquid, or gas. Now IR is very sensitive, so it can't do very thick samples. So 1 to 2 micron thickness of a liquid is enough to saturate, like absorb all the light. Okay, and Raman has trouble with colored samples. So because we use visible lasers, we can catch the sample on fire if it absorbs too much. And I've done that. It's not good. Okay. Now, rotational structure is not resolved in liquids or solutions or solids. So I think there's a homework question on that one. It says, what do you need for rotational structure to be observed? You need a gas phase sample because the molecule has to be able to freely rotate. So forensically, now Raman's really coming into play. And we'll talk about Raman in just a minute. So let's jump into this. So here's the Raman spectroscopy. It's a 2-photon process. We have the Rayleigh scattering and then the Raman scattering. And notice that we have this fundamental transition. So this will be the 0 to 1 spacing for vibrational differences, but we're using visible lasers. So those arrows are way too big to cause a direct absorption of the light. Okay. And I've kind of color-coded it accurately, right? If green laser comes in, a red photon comes out, okay? Because the difference between this vibrational difference from the green will give you that red photon. Now, if you have the molecule hot enough to have excitation in these excited states, you could get anti-Stokes Raman, and you get a blue photon in. Now, that's nice because that's a zero background technique if you can get anti-Stokes Raman. Here's automobile exhaust. And so we see a bunch of different peaks. We see some water. This is the vibrational and rotational lines of water. Okay, here's water also. We have carbon monoxide because we have some incomplete combustion. And so when you do your carbon monoxide lab, I've zoomed in on this right here and clipped that out, and that's your data that you have on Blackboard. And so you will analyze all of those little peaks. Those are the rotational lines on top of the vibrational transition for carbon monoxide. Then we have CO2 here, here, and then there's a Raman active mode of CO2. Now these over here are combination bands, and we'll learn about those. So these are also CO2. Combo bands. So here are the CO2 stretches. It's the animated. We have the symmetric stretch and the asymmetric stretch. We could go through the character table and see that, you know, this one is moving in the z direction. Okay, the dipole is oscillating back and forth in the z direction. This one is symmetric, and so that's like a z squared. And so this is Raman active only because it's A1G. The other one is A1U. All the ground states are A1G here. And so for this transition up here to A1U for the asymmetric stretch, okay, we can build that transition dipole moment integral. Z polarized light and A1G in the ground state. So Z polarized light is A1U. So A1G times A1U is A1U, and A1U times A1U is A1G. The integral over all space of that top row is not equal to 0, so there it's allowed. But we can't go directly from A1G to A1G because light is odd. Light is A1U, and so if we try to use that light to get to that A1G level, we're never going to be able to cancel out that U. And so that would be forbidden. So we can't go directly to the symmetric stretch in CO2 with light. We have to use the Raman effect. The Raman effect is a 2-photon effect, so if we come in with 2 Z-polarized photons, then we have a whole bunch of A1Gs and everything is allowed. Okay, so we're going to get some more experience with these normal modes of vibration, and I just want to show you some of them. So this is all of the normal modes and frequencies for acetonitrile. And so way down at low frequencies are the bending of the whole molecule. So you see the whole molecule is bending in half, specifically here. And this, again, it's got threefold symmetry. So the X and Y motions are doubly degenerate. And so way down there is nu 8, below 600 wave numbers. So we don't see that one. Then we have nu 4, where the whole, like again, the mass, the bigger the mass, the lower the vibrational frequency. And so this is moving a methyl group away from a nitrile group. And that's carbon-carbon bond is stretching. So a lot of mass is moving, so it's a low frequency. So that's around 900 wave numbers. Then we have the rocking, kind of rocking of that the CH3 group. This is really, light masses, but it's a real weak spring constant. And so it's not a lot of force pushing those hydrogens back into their equilibrium positions. So this is low frequency because it's a weak spring constant. This one is the umbrella mode. It's a very easily labeled mode. So whenever you see the hydrogens all moving together, kind of like an umbrella is blowing backwards, we call that the umbrella mode. Nu 6 is a deformation of the hydrogens. And again, it's a little bit tighter spring constant because the hydrogens are bumping into each other. This is the nitrile stretch. And so it's in a unique place right here at 2300 wave numbers, 2200 wave numbers. That is normally kind of a desert in infrared spectroscopy. There's really not anything that absorbs here except a carbon-nitrogen triple bond. So whenever you see a peak there, you know you have a nitrile. Here we're in the CH stretches region, and this is the symmetric stretch on the methyl group. And then at a little higher frequency, you have the asymmetric stretches. So does this show you, the take-home lesson is this should show you that every one of those peaks in the infrared spectrum is a different motion in the molecule. How many peaks should you have if every one of them was active in the infrared? In other words, how many vibrations do you have in a molecule? I heard somebody. What'd you say? Yes, 3n minus 6 vibrations. Three n minus 6 vibes. Okay. And so every one of those, if they're infrared active and the selection rules allow them to absorb light, they should have a peak. Okay. Now, what makes the peak tall or short is that transition dipole moment integral, which we can't calculate by hand. We can calculate whether it's zero or non-zero. So we can say, yes, it's allowed, so there should be a peak, maybe small. Okay. But Gaussian can calculate it. So we get the intensity from Gaussian, the IR intensities. And that's what's being shown down here. All of these little stick spectra are from Gaussian. And you can kind of see it works out. See, this one's shorter than that one. And it's not great, but this peak is a little shorter than that one. This is a pretty tall peak here. Okay, so it's not perfect, but it's good enough for us to assign the vibrational spectra. Benzene is a little more complicated, and you guys are going to do benzene. Here's all of the vibrations in the literature for benzene. It's really hard to see. This is out of Hertzberg, but a lot of times they have, looks like nothing's happening, but there's a plus and a minus. So the plus means that carbon atom's coming out of the paper, and a minus means the hydrogen's going back into the paper. Okay. I'm not expecting you really to use this. I'm expecting you to use the animations in Gaussian. So you can animate certain modes in Gaussian by loading up the output file. So you do the frequency calculation of benzene or chlorobenzene, and then you load that file into Gauss View and go over to results. And if you go to results, you'll see there's a selection called vibration. If you click on that, then you can video, like you can make an animation of the vibrations. So it's really, really cool. Okay, so let's look at the Raman set of notes. And this is also more about the spectrometers too. It's not just the Raman, but it's the spectrometers. So here we are in terms of vibrational spectroscopy. We're right here in the mid-infrared. That's where our spectrometer is, 400 to 4,000 wave numbers. That's where the fundamentals are for smaller molecules. They get into the far infrared for the whole molecule bending and so on. So those really low frequency modes, they get into the far infrared. But for the fundamentals for stretches, those are going to be in the mid-infrared. Here we are in terms of all of the different spectroscopic techniques. You can kind of see here this kilojoules per mole. You know, when we get into the visible range, we're roughly in the 1,000 kilojoule per mole range. And that's where you're breaking bonds, right? So that's the dissociation energies in the visible and in the UV. And that's why the UV is damaging to our skin and other materials, because it has enough energy to break bonds. But infrared light doesn't have enough energy to break bonds. It's in the 100 kilojoule per mole range. And so if you remember your organic, you know, all of those bond enthalpies, they were above 100 mostly. And so the infrared, the near infrared, or mid infrared specifically, like in the 60s of kilojoules per mole, that's not enough to break bonds. So we're just vibrating those molecules in their vibrational modes. The different sources here, in the UV we use a deuterium lamp, we use a tungsten halogen lamp in the visible, and then in the infrared we have a hot ceramic glow bar. So it's like a little ceramic resistor. We just put some voltage across that and it gets hot. And that's a pretty stable source. In fact, we leave it alone. We just keep it plugged in the whole time and it lasts for years, maybe up to 10 years. I like you to replace it after 5 or 6, but they go for a long time. Here are your essential equations and constants. And when you're using these in the lab, don't like measure with the micrometer and then use a constant that you could write with a crayon, right? I mean, if you're going to spend all this time in the lab or analyzing the data in Excel, don't use 3 times 10 to the 8 meters per second for the speed of light, okay? Because you've reduced it to one significant figure. speed of light isn't 3 times 10 to the 8. It's right here. It's 299792458 meters per second. Okay, so yeah, that's close to 3 times 10 to the 8 meters per second. But use all of those digits so that your constants aren't off and you get accurate data. Okay, so save this slide. Let's talk about dispersive instruments. The data for the infrared, data for the iodine lab was collected on a dispersive instrument. Most of our data is being collected on diode array detectors, though. But in instrumental, you'll get into this in much more detail. But you typically have a diffraction grating and a slit. And so to get higher resolution, you narrow this slit to let a smaller band of color through, a smaller band of light. And so for higher resolution, you have a less light and less signal to noise. You can replace that slit with a diode array detector and collect all your data very quickly. But each one of these diodes is a separate detector. And each one of those diodes has a different noise level. And you'll see that when you work or see the demos on the Raman spectrometer in the lab, is you'll see the dark noise and you'll see how noisy it is. Okay. So one way to get past that high resolution, reducing the signal that you get, is to go with a FT technique. So these interferometric spectrometers are really fantastic. You've got this source here emitting, like I said, 100% of that light coming off the source goes through this beam splitter, and 50% goes towards a fixed mirror and 50% passes through to a moving mirror. And then that moving mirror goes back and forth, and you measure its displacement in centimeters. Now, this is what I call a resonant cavity. So if this confuses you, it's like, how does that 50% up and 50% over light recombine at the beam splitter and 100% come out? It's like ringing a bell. Okay, this interferometer is resonating with all of the different frequencies of light, and so they're recombining and coming out with a very high brightness, and they go through your sample and through the detector. Now, FT instruments are single beam instruments, so you have to take a background, and then you have to take your sample, and then you have to do the ratio separately. Okay. But the resolution does not depend upon any slits, so you're never reducing the amount of light going through this interferometer. Okay, what you're doing to get higher resolution is you're moving this mirror a longer path. And so this is the signal that you get. You get this interferogram, and I've shown 2 cosines on here. And notice that as the mirror displacement moves, you get at the beam splitter, you get positive and negative interference. So in this case, the red cosine, let's say this mirror displaces 1 centimeter. This red cosine has gone down through 1 full length as it went to its fixed mirror and came back. And then the other wavelength has gone down and back, but it's only because it's a longer wavelength, it's now at its minimum. And so the minimum of that light cancels out the maximum of that light, and you end up with 0 light coming through. If you only had 2 wavelengths of light, there'd be points in the interferogram where you would have no light, where they cancel out. And then sometime later, they would be back in phase, and you'd have a bright spot again. And then they'd be out of phase, and you'd have a 0 again. And you'd have some negatives, and you'd have some positives, and so on. So this is what's going on with this interferogram. Now, there was a mathematical way to take this signal and do a Fourier transform to pull out the signal of the cosines. And whatever method you're using, if you're collecting your data, say in terms of wave numbers, the Fourier transform always inverts this. Oops. Let's see. So you see this now, the x-axis or horizontal axis is inverted wave numbers. So if you're collecting your interferogram by distance in centimeters and you do a fast Fourier transform on it, you get out wave numbers. Okay. Now wave numbers are number of waves per centimeter. And so can you get can you label these 2 peaks here? So we have two frequencies in our interferogram. What are those two frequencies? So let's just pick the red one. The red one goes down and back in 1 centimeter. So it's 1 cycle per centimeter. Per centimeter, that's a wave number. So it's 1 wave number. And so this might be 1 right here. And then this other one goes down and back in 2 centimeters. So in 1 centimeter, it's a half of a wave per centimeter, right? It's 1/2. It has to have 2 centimeters before it goes down and all the way back up. So it would be 0.5. So those are the two peaks that we would have in that interferogram. When we do the fast Fourier transform, all this interfering signal gets decomposed into its frequencies, and then we would see the two peaks that we have. So that's what's going on with our Fourier transform instruments. So what's happening in the infrared spectrometer, that's a silly video, but it's to show at the ATR, we have the source, we have the interferometer, and then we have this attenuated total reflectance. So notice the light doesn't go through our sample. It bounces off this diamond here. And it's totally reflected at the undersurface of that diamond. So it goes into the diamond and it bounces and it's totally reflected. So that's what the total reflectance part is. So we've got the right angle for this light hitting this diamond underneath, and it bounces off. And so we get 100% of the light reflected on the underside of that diamond. Now, what's happening to the electrons in that diamond? They're shaking a little bit. And so it's like a trampoline, that where the diamond surface is, the surface of that diamond, the electrons in that diamond are shaking like that with the light. Okay. So it's really backwards from what you think a trampoline. For a trampoline, you're making the surface vibrate. But in this situation, the trampoline is vibrating. And if you're on that trampoline and it happens to hit the vibrational frequency of your legs, then your legs would start shaking like this weirdo. Okay, so his legs, it's hitting the vibrational frequency of his legs. His body's not really vibrating at that frequency. You see how his body's staying kind of at the same elevation. But it is that frequency of the trampoline has been absorbed by his legs. And that's the attenuated part. It's attenuating that frequency. So when it hits the detector, that frequency is missing. So that's what's going on with the ATR. The light is vibrating the surface of the diamond, just the electrons in the surface of the diamond, or really maybe even the atoms in the surface of the diamond, and then the sample sitting on top of that. And if it happens to hit a vibrational frequency of one of the bonds in that sample, it can steal some of that light. Okay, so I just typed in trampoline, silly legs or something like that, and this popped up. So you can find anything on the internet. So we have all those fundamentals. Every one of those peaks is a different fundamental, and this is just showing you how we would label those with the quantum numbers. You see, I've taken the vibrational spectrum, which is normally like plotted with the horizontal axis horizontally. I've turned it sideways and plotted it here, and you can see where those peaks show up is where there's vibrational energy levels. You see that? And every one of those vibrational energy levels is a different quantum number. So this is the V1 quantum number, and V2, 3, 4, and 5 are 0. So we've got just the fundamental for V1. And this is the V2 fundamental. All the others are 0. And that's the V3 fundamental. So wherever there's a vibrational level, that's where we would have a peak in the spectrum. Now for Raman, it's a 2-photon process. And so in this case, for say a CH stretch, we hit it with 532 nanometer light and 633 nanometer light comes out. It's bizarre, right? We send in green light and red light comes out of our sample. Where did that come from? Okay, it's called inelastic scattering. There's a whole lot of green light that comes out. That's called Rayleigh scattering. So it's elastic scattering. It hits the molecule and bounces off. But some of the light is redshifted and by the Raman effect. So this is Raman, not Ramen. It's not the noodles. Okay. So if you put that in your report, you'll get a nasty little note. Okay. He used sunlight and a filter in the human eye as a detector. So he discovered the technique, and it's been named after him. It was not very popular because it was really expensive and bulky. But this is the Raman spectrometer I used in grad school. So that's me with my Texas jalapeno shirt on. Okay. And that was the laser right there. And the power supply was over here. It's about the size of a washing machine. Okay. And so it was big and bulky, not very useful for forensic analysis. Now these things with diode lasers can be toted around with battery pack. And so Raman has really come in to forensics because it can shoot through glass. You don't need to touch the sample. Hey, I like that. If this is a potential fentanyl powder, I'm gonna shoot it with a little ray gun. I'm not gonna touch it. Okay. It can go through packaging. So if you got a blister pack of some pills, I can shoot the Raman visible light through a clear pack and see what pill that is. See if it's counterfeit or not. Okay. So again, this 2-photon process is the Raman scattering process. We have the transition dipole moment integrals use all of the second order combinations of X, Y, and Z. And so we can use the character tables to figure out if the Raman mode is active. And so here's the same thing for the Raman spectrum, showing all of the fundamentals. Okay. So this is still the same fundamental transition, but notice we didn't get there with an up arrow. Okay. We used the green light and we got red photons out. And those red photons show up wherever there's peaks in the spectrum. This is a schematic of what we do. Most of the light is not changed. And so we throw away all the green light and we collect the red and orange light. Just give me one more minute. Okay. We have a diode array Raman spectrometer. So we have a fiber optic, and that's the only thing that you can screw up in this lab. If you're in there playing with it, with the TAs, of course, just don't ever kink the fiber optic because it's a glass fiber, and if you kink it, it'll break. Okay, so just be gentle with it. So I'll put this calculation in your notes. I don't think you have it filled out, but here it is, and it'll be on the video. Okay, so you can go in. But whenever we're working with wavelengths of light, we need to convert them to wave numbers to calculate the scattered light. So this is one of the questions on your lab report. So the laser line is 532 nanometers, and so we convert that to wave numbers, we get 18,000 wave numbers. That's what visible light is, and it's in the thousands of wave numbers. Then for the CH stretch, we're going to subtract 3,000 from that because it's redshifted. Okay, so it's going to be lower in energy. So we subtract the 3,000, so we get to 15,000 wave numbers, and then we can convert that back to nanometers, and then we see that it's a 633 nanometer photon of light. So it's still visible, still goes through glass, still goes through clear plastic. And so we can get infrared or vibrational information inside a plastic caplet or inside a glass vial. And that's great. We couldn't do that with infrared. We have to actually take the sample out of the packaging and analyze it on the spectrometer to do infrared. So we can still get vibrational spectroscopy. We can still search libraries. So this is really good for forensics. Diode laser Raman is fantastic. Okay, so that's pretty much it for this.